Hello everyone. In this video we look at one of the important types of collisions, which is elastic collisions. Now elastic collisions are those type of collisions where the total kinetic energy of particles before the collision will be equal to the total kinetic energy of the particles after the collision. Now we'll try to deal with these elastic collisions in two categories. One, the elastic collisions in case of the head-on type of collision, and second, the elastic collisions in case of the oblique type of collision. Now here we have an example of what is an head-on collision. Let us say we have two bodies of masses m1 m2 which are moving with initial velocity u1 and u2 in the same direction. Now it is possible that the two bodies m1 and m2 might still have a head-on collision by moving in exactly opposite directions. The thing is, like the way we deal with in the 1D motion, if we consider both of them to be in the same direction, then both the values we will take it as positive by following the sign convention. If they are in opposite direction, means if we take one of them to be positive, if we give the values in one direction to be positive, let us say we take the values towards the right side to be positive, then the values towards the left side will be taken as negative. That is going to be the only change that we have to do in case of the case where we have the velocities of the particles in opposite directions. Now let us say after they collide with each other, the final velocities are becoming v1 and v2. When we look at collision, any collision in general, it will be satisfying the law of conservation of momentum. So if you apply law of conservation of momentum, here assuming that all these velocities are in the same direction, what we have is momentum before the collision m1 u1 plus m2 u2 will be equal to momentum after the collision, which will be m1 v1 plus m2 v2. So we will call it as equation 1, which is the law of conservation of momentum. Now since we are referring to this head-on collision as an elastic head-on collision, the total kinetic energy of the particles before must be equal to total kinetic energy of the particles after, which would mean half m1 u1 square plus half m2 u2 square, which is the total kinetic energy of the particles before the collision, will be equal to half m1 the v1 square plus half m2 v2 square. Now here we can cancel half on both sides and bring the terms m1 together. So we'll bring m1 v1 square to the LHS and we'll take m2 u2 square to the RHS. Thereby what we'll have is m1 into u1 square minus v1 square will be equal to m2 into v2 square minus u2 square. Now this is the equation that we will be having. The first equation can also be written by taking the values of m1 to one side and m2 to the other side. So if you rewrite the first equation, what we'll have is m1 into u1 minus v1 will be equal to m2 into v2 minus u2. Now let us call this as equation 3, or rather equation 2 and equation 3. If we divide the equation 2 with equation 3, what we'll have on the LHS is the m1 and m1 will be cancelled. u1 square minus v1 square can be written as, it's a square minus b square type. It can be written as a minus b into the a plus b. So the a minus b and a minus b term, which is u1 minus v1 and u1 minus v1 will be cancelled. Finally what will be left with is u1 plus v1. Similarly on the RHS side, when we divide equation 2 by equation 3, what we'll have is the m2 term will get cancelled, and this v2 square minus u2 square can be also written as v2 minus u2 into v2 plus u2. So after the division, what we will be left with is only v2 plus u2. Thereby, if you want to just bring the initial velocities onto the one side and final velocities onto the other side, what we would have is, by bringing u2 to the LHS and v1 to the RHS, u1 minus u2 will be equal to v2 minus v1. Now remember, we have talked about this coefficient of restitution, which is modulus of v2 minus v1 by modulus of u2 minus u1, the relative velocity of separation after the collision divided by the relative velocity of approach before the collision. So if you see, the value of v2 minus v1 is equal to u1 minus u2. So if you take a ratio of the two, the value will be coming as 1, which means for an perfectly elastic collision in the head-on type, the value of coefficient of restitution will be equal to 1. And we'll see what will be the coefficient of restitution when we go to the other types of collision, which is the inelastic collision or perfectly inelastic collision. So we'll be able to discuss about it, but in general, for an inelastic collision, the value of the coefficient of restitution will be between 0 to 1. As we see in the case of perfectly elastic collision, it will be 1, and we'll see that for the head-on type of collision, the value of E in case of an perfectly inelastic collision will be 0. So we'll talk about how the E values will be changing in case of other type of collisions, but for this elastic collision head-on type, the value of coefficient of restitution will be equal to simply 1. Now we'll try to use this relation, which is u1 minus u2 is equal to v2 minus v1. Let's call it as equation 4, and try and derive the values of v1 and v2, which are final velocities of the particles after the collision. So what we can do is, we have u1 minus u2, which is equal to v2 minus v1. Now if you want v2, by bringing the minus v1 onto the LHS, it will be v1 minus u1 minus u2. This will be equal to v2. Now this is the value of v2, which we can take and substitute in the momentum equation. So momentum equation is m1 u1 plus m2 u2 will be equal to m1 v1. Total initial momentum is equal to total final momentum. In this equation, there are two unknown variables, v1 and v2. We'll substitute the value of v2 as v1 minus u1 minus u2. In this equation, when we substitute, the equation will be fully having only one variable, that is v1. On solving it, we'll get the value of v1 as m1 minus m2 divided by m1 plus m2 into the u1 plus 2m2 by m1 plus m2 into u2. Similarly, the formula for v2 will be symmetric. It will be m2 minus m1 by m1 plus m2 into u2 plus 2m1 by m1 plus m2 into u1. So these are the final velocities of the particles after the collision. Now here we have assumed that in this head-on type of collision, the energy value of particles, total energy, kinetic energy of particles before the collision is equal to total kinetic energy of the particles after the collision. And only in this particular case, these velocity values will be holding true. We look at some special cases in this head-on elastic type of collision. So let us say we have a collision where there is an object m2 and there is an object m1. So typically the object which is coming and approaching faster, we call it as a projectile, and the object which is getting hit, we call it as a target. I mean, that is the nomenclature that we generally follow. So let us say we have both projectile and the target having same mass. m1 is equal to m2. Let us say the value is equal to m. Now in this formula, if m1 is equal to m2, the first term will become 0, and m1 is equal to m2, so v1 value will be equal to, numerator we have 2m, denominator m1 plus m2, because both are equal to same mass, so denominator also 2m into u2. So what we have is V1 is equal to U2, and in case of V2, since M1 is equal to M2, this term would become 0, thereby and the second term again will be having 2 times of M. By denominator M1 plus M2 will be, both are equal to M, so M plus M, 2M it will become into U1. So 2M will be cancelled. So we have an interesting result. That is, if we have the head-on collision which is happening between two particles of identical mass, then the velocities of the particles after the collision are simply getting exchanged, which means V1 is equal to U2 and V2 is equal to U1. So just to look at what will be the kind of situation. Let us say we have an object of mass M. It's going with 10 meters per second speed. It's a projectile. There is another mass equal which is going with 2 meters per second. Now after the collision, what would happen is, let us call this particle 1 and particle 2. After the collision, the velocity of the particle 1 would become 2 meters per second, and the velocity of the particle 2 would become 10 meters per second. So this is the significance of the head-on collision in case of the elastic category. Now we can even have another special case within this. Let us say we look at the billiard ball collisions. Generally speaking, the collision between the billiard balls are not elastic in nature truly, but if we assume them to be elastic, let us say the ball is moving with a velocity u, and this is initially at rest, means the velocity will be 0. Then after the collision, what we would see as per this result is the objects must exchange their velocities, which would mean, so this is the first ball which is coming and the second ball is at rest. After the collision, what we would see is the first ball would come to rest and the second ball would start moving with whatever is the initial velocity with which the first ball is coming. So these are some of the special scenarios which we can have in case of head-on elastic collision between particles of equal mass. Now let us look at a situation where there is a massive projectile which is colliding with a light target. So as we have been saying, the convention that we are using is the particle M1 is the projectile which is approaching faster and hitting the other particle M2, which we are calling as the target. So here the projectile mass is heavy, which means the M1 value is very high in comparison to M2. Now what will be the significance of this? The significance of this will be, we can neglect the value of M2 in comparison to M1. So let us look at the velocity of the projectile, which is the first particle after the collision. So in this formula, since M2 is very small, we can neglect this value of M2 and this value of M2. So the first term would simply become M1 by M1 into U1, which is U1. And the second term, since M2 is going to be very, very small in comparison to M1, the numerator value will be very small in comparison to the denominator. So denominator we have M1 plus M2, which will be nearly equal to M1 because M2 is very small. So we can totally neglect the second term because it will be very, very small. So what we are concluding is V1 will be equal to U1, which means there will be no change in the velocity of the projectile, which is heavy, after the collision. Let us come to the V2 side of it. V2 will be equal to, as per the head-on elastic collision formula, M2 minus M1 by M1 plus M2 into U2 plus 2M1 U1 by M1 plus M2. Here M2 is negligible in comparison to M1, so we'll neglect it. So we have numerator minus M1, denominator by M1, which is minus U2. That will be the first term. Second term, since we can neglect M2 in comparison to M1, what we have is 2M1 by M1 into U1, which is 2 times U1. So V2 value we can write it as 2U1 minus U2. So these are the velocities of the particles after the collision. Now we can look at this with an simple illustration. Let's say we have Zeep, which is having a mass of 10 power 3 kg, approaching a cyclist who is having a mass of 60 kg, and the velocity of the Zeep is 120 kilometers per hour and velocity of the cyclist is 10 kilometers per hour. Now we can take the Zeep to be the heavy projectile, and this is a light target. So what we will be able to see after the collision approximately is the Zeep velocity, which is 120 kilometers per hour, will remain unchanged, which means the value of V1 will still be approximately 120 kilometers per hour, and the value of V2 will be equal to 2U1, which means 2 into 120 minus U2, which is 10. That will be 240 minus 10, which is 230 kilometers per hour. So we see that after the collision, the cyclist would start moving with a very high speed, which is equal to 230 kilometers per hour. So this is what we have in case where the projectile is very heavy in comparison to the target. Now we can look at another case where the projectile is light and the target is very heavy, which means as per our convention that we are using, we are going with the idea that M1 is the projectile and M2 is the target. I mean, the reason why we are using the word projectile and target is because it is supposed to approach with a higher velocity and hit the M2. That is the reason why we are using the word projectile for this. So here, since the projectile is a lighter one, the value of M1 is supposed to be very small in comparison to M2, which means in the calculation we can neglect M1 in relation to M2. So we'll go to the final velocities of the particles after the collision, which we have derived from the elastic head-on collision base derivation. So we have V1 is equal to M1 minus M2 by M1 plus M2 into U1 plus 2M2 by M1 plus M2 into U2. Now here we can neglect M1 in comparison to M2, means in the first term when we neglect M1, what we will be having is V1 is equal to, so minus M2 by M2 will be minus U1. The second term, if we neglect M1, so what we will be having is plus 2U2, because it will be 2M2 by M2, which will be 2U2. So this is the velocity of the projectile, which is a lighter one after the collision. Now the velocity of the target, which is a heavier one, M1 we will neglect, so V2 will be equal to, the first term will be M2 by M2 into U2, which is U2, and the second term, since we neglect M1, the numerator will be very small in comparison to denominator, so thereby the second term value will be almost negligible. So what we have is V2 is equal to U2, which means in this case, which is reciprocal to what we already saw before, the target would get undisturbed and it will continue to move with whatever is its initial velocity. Now we can look at a special case of this where if the target is at rest, means we have a situation where there is a wall or something which is very heavy and a ball is going and hitting the wall. So the value of U2 will be 0, and the situation that will come out of it will be, if U2 is 0, then in the first formula the velocity of the projectile V1 after the collision will be simply, if U2 is equal to 0, then V1 will be equal to minus U1, and since U2 is equal to 0, V2 also will be equal to 0. So which means what we observe is the ball will be rebounding with the same speed but exactly in the opposite direction. That is the reason why the velocity is recorded as negative, and the stationary wall which is at rest initially will remain unchanged. So this is one of the special case that we will be observing in case of the head-on elastic collision, where the projectile is a lighter one and the wall is a heavier object. And usually this is what we see in case of collisions of gas particles with the container walls. The next type of collision is the oblique collision. So head-on collision would mean that the particles have their velocities along the same line. Means the particles which are undergoing the collision, we saw either they are moving in the same direction along the line, or they may be moving in opposite directions but still along the same line. So such a type of collision we call it as head-on collision. Now oblique collision is where the particles may be moving in 2D space, or they may be moving in 3D, and they will undergo collision. And usually in case of oblique collision, it becomes difficult to solve the problem for the simple reason that we'll be having more number of unknown variables, and we would definitely be requiring some more experimental data than just the equations to solve for the variables in case of an oblique elastic collision. But nevertheless, what we'll do is we'll try and take a look at one of the simple cases of the elastic collision where we have one particle which is moving along a particular direction would collide with another particle also moving along the same direction, but the velocities are not in the same line. Then what would happen is, after the collision, both the particles will start moving in a plane. So we call this as glancing type of collision. And what we see over here is the initial velocities of the particles will not be in the same line, but they will be in the same direction. But the final velocities, let us say the final velocity of the particle 1 is making an angle theta with the horizontal, and the final velocity of the particle 2, which is v2, is making an angle phi with the horizontal. So let this be the representation of the velocities after the collision. Now, like the way we talk about the conservation of momentum in every type of collision, we can talk about the conservation of momentum in this collision as well. But here, when we look at momentum, since it is a vector, we can talk about the conservation of momentum along both the horizontal direction as well as the vertical direction. So if we take let us say this to be the x-axis and this to be the y-axis, we can talk about the conservation of momentum both along the x-axis and y-axis. So first, when we look at the conservation of momentum along the x-axis, what we would have is the initial momentum of the first particle m1 u1, the initial momentum of second particle m2 u2 will be equal to the component of the momentum of first particle after the collision will be m1 v1, but its component along the x-axis will be only m1 v1 cos theta, and the momentum of second particle after the collision will be m2 v2, but it is along this direction. The component of it along the x direction will be m2 v2 into cos phi. So this will be the conservation of momentum relation along the x-axis. Now when we talk about the y-axis, since initially both these momentum, the momentum of the first particle as well as momentum of the second particle, they are confined to the x direction, initially there is no y component of the momentum. Means the initial y component of momentum value will be 0. And in the final state also, when we add up the y component of the momentum values, they must give us a result 0. So what we have is the initial y component of the momentum 0 should be equal to the y component of the momentum of first particle after collision will be m1 v1 into sin theta. We can see the component will be coming along this direction. If we resolve, the x component is m1 v1 cos theta and y component will be m1 v1 sin theta. So it will be along this direction. But when we take the vertical component of the momentum of second particle, we see that it will be coming in the negative y direction. The value will be m2 v2 cos phi, but it will be in the negative y direction. Since momentum is a vector, we have to take it along with the direction. So if we take the positive y to be plus, then the negative y should be taken as minus. So the total final y component of the momentum will be m1 v1 sin theta minus m2 v2 sin phi. The value of both of them when we add, it should be equal to total initial y component of the momentum, which is 0. Now since we talk about elastic collision over here, we'll have total initial kinetic energy is equal to total final kinetic energy, which means when we add the kinetic energies of the particles before the collision must be equal to the kinetic energy of the particles after the collision, which would mean half m1 u1 square plus half m2 u2 square will be equal to half m1 v1 square plus half m2 v2 square. Now as you see here, we have like too many variables. We have a variable v1, we have a variable v2. I mean, assuming that the known variables or quantities are m1, m2, u1 and u2. The unknown variables in this case will be v1, v2, as well as the theta and phi, the values, the angle over here theta as well as phi. Both are also unknown variables because we would not know in what angular directions both the particles will be leaving after the collision. So we have 4 variables and just 3 equations, which means it is difficult to solve the variables unless we have some experimental data given. And that is the reason why to solve the case of the collisions where the particles are moving in a 2D or a 3D space, we would require definitely some experimental data to solve the variables. But if we take a special case where the value of m1 is equal to m2 and u2 is equal to 0, which means both the particles are having equal mass and the second particle is at rest. If you go with that kind of a situation, then we'll see that let us call these equations as equation 1, equation 2 and equation 3. We'll see that the equation 1, 2, 3 would get simplified. How they would get simplified? The equation 1, if we take u2 to be 0 and m1 is equal to m2, on either side the mass values will get cancelled, and finally what we have is u1 is equal to v1 cos theta plus v2 cos phi. So we will call it as equation 4, and equation 2 would get modified as we have on the LHS 0 and both mass values are same, so we can take them onto the left hand side. So the remaining part is 0 is equal to v1 sin theta minus v2 sin phi, which we can call as equation 5. And the equation 3 can get modified as, since all the masses are same, we can cancel off half as well as the mass terms, since we are assuming that the m1 and m2 are same, and u2 is 0, which means what we'll be having is u1 square will be equal to v1 square plus v2 square. So we will call it as equation 6. Now we'll see that when we square equation 4 and 5 and add them, so squaring equation 4, LHS will have u1 square, here LHS 0 square will be 0, will be equal to, when we square it, so we'll be having v1 square cos square theta v2 square cos square phi plus 2v1 v2 cos theta cos phi. This term will be having v1 square sin square theta plus v2 square sin square phi minus 2v1 v2 sin theta sin phi. Now if you see, we have v1 square cos square theta and v1 square sin square theta. When we add both of them, we'll take v1 square common out. Cos square theta plus sin square theta will be equal to 1. v2 square cos square phi, v2 square sin square phi. When we take v2 square common out, we'll be having cos square phi plus sin square phi, which will be equal to again 1. And here we have 2v1 v2 cos theta cos phi minus 2v1 v2 sin theta sin phi. If you take 2v1 v2 common out of these two terms, we have cos theta cos phi minus sin theta sin phi, which will be equal to cos of theta plus phi. It's a trigonometric property. So cos of theta plus phi will be equal to cos theta cos phi minus sin theta sin phi. So the final result that we'll be having is u1 square on the LHS is equal to v1 square plus v2 square plus 2v1 v2 cos of theta plus phi. And this when we try to compare, let us call this as equation 7, when we try to compare equation 7 with 6, what we'll be having is, since equation 6 is saying u1 square is equal to v1 square plus v2 square, equation 7 is saying u1 square is equal to v1 square plus v2 square plus 2v1 v2 cos phi, which means the third term should be having a value 0, which means the cos of theta plus phi must be 0, which means theta plus phi value must be equal to pi by 2. Now what is the result that is coming out of it is, when we have this elastic glancing collision between two particles of equal mass, where the second particle is at rest initially, the particles would project, or they would be receding in such a way that the two angles that they make with the horizontal will be complementary to each other. When we add both the angles theta plus phi, it is equal to pi by 2. But as such, analyzing an oblique collision with the elastic collision property, we will not be able to find out all the values of the variables, because we'll be having lesser number of equations and more number of variables. So if you have only some experimental data to support, we will be able to solve for these variables. So this is about the elastic collisions.